Okay, let's continue our section 8.4. Now let's coming back to see how we can use the matrix inverse to solve the system of equations with unit solution. Is an invertible. The system of an equation. And here we are focusing on the linear equations. Equation x is equal to A inverse times B. Let's take a look how this one comes from. Think about AX equals B. If I multiply both sides of the equation by inverse of A, remember the definition of inverse. A inverse times A, that's identity matrix. So identity matrix times X equal A inverse B. And any matrix times the identity matrix, the matrix itself. So X equal to A inverse times B. For matrix multiplication, we don't have the commutative property. Make sure you don't switch the order A inverse and B. Let's take a look at this example. There's nothing better to learn and during by using an example. We are going to solve this system equation. Let's use a 3 by 3. X minus y plus 2z equals 16. Negative x plus 3y minus z equals negative 15. 2y plus z equals 13. So this is the equation. We have learned substitution method, elimination method, Gaussian elimination method, and Gaussian Jordan method. But right now we are going to use the matrix equation. First, we are going to learn how to write it as a matrix equation. The AX equals B. A is the coefficient matrix, where you store every coefficients into this matrix. And X is not really the X, this is X including X, Y, and Z, so it's the unknown matrix. And B is the right hand side, so this is right hand side. Let's take a look at our problem, how to write our matrix equations. Let's see. Well, columns are the corresponding variables, coefficients, and row is the corresponding equation, just like the Armantine matrix. So X coefficient is 1 for the first equation, Y coefficient is negative 1, 2 coefficient, Z coefficient is 2. The second one is negative 1, 3, negative 1, 3, 2, and negative 1. The unknowns are X, Y, and Z. I say X, Y, Z. That's equals to the right hand side 16, 15, and 13. If you don't think this is right, you can double check by using multiplication. When you multiply the matrices, use the row multiply column. 1 times X plus negative 1 times Y plus 2 times Z equals 16. That's exactly the equation 1. So and so on, you can get equation 2 and equation 3. Now, if I want to find X and Y and Z, then I can use this inverse idea, which is if I can find the inverse of this matrix 1, negative 1, 2, negative 1, 3, negative 1, 3, 2, 1, find the inverse this matrix, then I use that to multiply by the matrix B, which is a vector 16, 15, and 13. I'm going to pull this part out, looking for the inverse. Let's try focus on how to find this inverse. When you find the inverse of matrix, we can use the Armantine matrix, the Gauss elimination method or Gauss-Jordan method. Replace the matrix on the left-hand side of the Armantine matrix and put the corresponding identity matrix to the right-hand side of the Armantine matrix, and use row operation to move the identity matrix to the left side. The first element is already 1, so we don't have a big issue for that. And that will become our pivot, right? So use that to clear the elements below the pivot. So the first row remains the same. The second row will be changed by adding row 1 and row 2 and replace row 2. So that will be 0, 2, 1, 1, 1, 0. The next one is 3, so I need to make this one as -3. So -3 times row 1 add into row 3 to replace row 3. 3 plus -3, that's 0. 2 plus -3 times -1, that's positive 3, that's 5. 1 plus -3 times 2, that's -6, that will be -5. 0 plus -3, so that's -3. 0 plus 0 still 0. 1 plus 0 is 1. Okay, now we move on to the next one. The next one is 2. We need to make this one as 1. We can divide both the entire row by 2. So row 2 divided by 2, keep that as a fraction. 1, -1, 2, 1, 0, 0. That is the first row. Second row is 0, 1, 1 half, 1 half, 1 half, and 0. Third row is 0, 5, -5, -3, 0, 1. Okay, we are going to use this pivot to clear this one and that one. The first row, we can just use row 2, add into row 1 to replace row 1. Okay, again, row 2 is your pivot, so we are going to keep it. And row 1, let's add them, so it's 1, that's 0. 2 plus 1 half, that is 5 half. And 1 plus 1 half, that's 3 half, that's 1 half. And this is 0. To make this one 0, we need to have the pivot as -5. So we use -5 times row 2 and add into row 3 to replace row 3. So that is 0. That's times -5 plus 5, that's 0. And -5 half plus -5, that's -15 half. -5 half plus -3. -3 is 6 half, so that's -11 half. And the next one is 1 half times -5, so -5 half. And this one is 1 right here. Move up to the next one to make sure this one is 1. So you use row 3, multiply the reciprocal of that number, -2, 15, to replace row 3. So that will be 0, 0, 1. And this one negative capacity, so that will be 11, 15. Negative capacity, that will be 1/3, and -2, 15. Okay. Now we are going to use this as a pivot to clear these 2 rows elements. You can see the problem is not always nice like having integer. A lot of times we deal with fractions. So to clear the first one, we use -5 half times row 3 add into row 1 to replace row 1. Let me copy the row 3 down so I won't mess up with that. Okay. If you are having problem to keep track of those numbers, as I suggest that to do the row operation, you can use a piece of paper, you scratch paper to record each row operations. Right, so now let's take a look. I need to use negative 5 half times row 3 and then add into row 1. So that's 0 plus 1 is still 1, 0 plus 0 is still 0, and this is negative 5 half plus 5 half is 0. That's what we want. And the complicated one is right here, so you will use negative 5 half times 11, 15, and add into 3 half, and we get negative 1/3 right here. Similarly, we use negative 5 half times 1/3, add into this fraction 1 half, and we will get 1/3 of this as a negative 1/3. The next one, similarly, you use the negative 5 half times this element negative 2, 15, and add into this element with 0, which is we get 1/3. Alright, so the next one we need to clear the 1/2 using the similar idea, using negative 1/2 times row 3, add into row 2 to replace row 2. So 0, 1, 0. And we are going to use negative 1/2 times 11, 15, and add into 1/2. We got 2/15 right here. And the next one is using negative 1/2 times 1/3, add into 1/2. We get 1/3 in here. And the last one is negative 1/2 times negative 2/15, and add into 0. Then we will get 1/15 out of this. So that is your A inverse, which is the matrix inverse of the coefficients. Then what's in my x, y, and z? Of course, before you move on to the next step, maybe it's better for you to check if this is a V inverse in here. But in the lecture, I'm going to skip that part, leave you to check that. I'm going to use the A inverse with this I get, and multiply the B matrix, which is we got is 16, 15, 13. Right, let's check the dimension. This is 3 by 3 matrix multiplied by 3 by 1. So your result should be a 3 by 1 matrix. Remember, in each location, row, this is first row, first column, so you will use first row from first matrix and first column from the second matrix, multiply them together, multiply the corresponding one, and add those numbers together. And eventually, you will get into 4, -2, and 5 in here. From the matrix equality, then we can know the corresponding position elements should be equal to each other, which means x equal to 4, y equals to -2, and z equals 5. So that is our solution. This is how we use the matrix equation to solve the linear system. Indeed, for the 2 by 2 matrix, we have a shortcut to find the inverse of the 2 by 2 matrix. I'm just going to share with you the shortcut for the 2 by 2 inverse. Okay. Unfortunately, when you go up to more than 2 by 2, there's no such shortcut for that. So using the Gauss-Jordan method is always a safer way to find your inverse of the matrix. If I have a matrix, let's say it's A, B, C, D, then A inverse is equal to, this is a diagonal, you multiply the main diagonal and subtract the elements from the minor diagonal, multiply them together. And the main diagonal, you are going to switch the positions of D, A, and then the minor diagonal, you can take the opposite number. So that's how we find the inverse for the 2 by 2 is a little bit shorter, right, instead of doing the Gauss-Jordan method. For instance, if I want to find a 2 by 2 matrix, for instance, is 5, -1, 3, 1. We want to find the inverse of this matrix. You can use the Gauss-Jordan, and also you can use the shortcut one to find it. We get 1 over the main diagonal, 5 times 1, subtract the minor diagonals product, and switch the main diagonal position, and take the opposite of the minor diagonals. 1, 3, -3. Sorry for the screen. That's something happened to my computers. And let's continue working on this problem. That will be 1 over 8 times 1, 1, 3, 5. Well, this is not really your inverse yet. You need to do the scalar multiplication, multiply the 1/3 by every element inside your matrix. So it's 1, 8, 1, 8. Oh, I copied without the negative 3, 8, and 5, 8. Alright, that will conclude our 8.4, and later on I can send you more reference for these lessons.